So if you get this far and you appreciate that now you have an equation, the next step, of course, just like for Newton's equation, is to solve the equation. What that means is, what you want to know is the metric on space-time. So the metric is what you need to actually calculate the force on a rocket ship or a planet or whatever, or a black hole, okay? The metric is implicit here because you use the metric to define the Riemann tensor and the Riemann tensor to define the Ricci tensor and the curvature scalar, but it's a little indirect. In fact, it's kind of like super duper indirect. So just to let you know, I've written out one component of the Riemann tensor in terms of the metric. Here it is. So in principle, you could say, all right, I'm going to be plucky. You assign your least favorite graduate student the job of trying very hard to solve this. And Einstein himself realized the level of complication, the number of mathematical operations you have to go through to go from metric to Riemann and back and forth and solve his equation. And he said this, no one's ever going to do this. I'm not going to do this, and I'm Einstein. So no one else is going to do this. Carl Schwarzschild went and did it. Schwarzschild is a fascinating story. He was an astronomer and mathematician by trade, but it was, remember, look at the dates on this. 1917. There was a war on, you might remember, right? World War I. And Schwarzschild, because he was good at math, was given the task of calculating ballistic trajectories for the Germans fighting the Russians on the Eastern Front. But they were, I don't know what the details were, but apparently there was shore leave or something. And it's not the Navy, so it's not shore leave, but he had some time off from fighting at the front, and he was allowed to go to Berlin, and he spent his time off listening to lectures by Einstein on relativity. It's a choice. You can't argue that. And Einstein gives his equations, and he says no one's going to solve them. Schwarzschild goes back to the front, and he sits down and solves them. And so how can you possibly do this? Well, you make a lot of guesses. You make a lot of assumptions, right? You say, that doesn't sound very sciencey. I'm going to use the German word. I'm going to call it an Ansatz. An Ansatz is a guess. And in this case, what Schwarzschild said is, look, I don't care about the general arbitrary solution to anything. I care about the Earth moving around the sun. So I'm going to ignore, actually, the Earth and Jupiter and everything. I'm going to take the sun, put it in the middle of my coordinate system. I'm going to use spherical coordinates, just like we talked about. So rather than t, x, y, z, it's t, r, theta, phi, as you can see in the equation up here. And I'm going to assume all the off-diagonal elements are zero, and et cetera, et cetera. And I'm going to assume everything is static, nothing is vibrating. And then he actually whittled the problem down to something you could actually solve. And this expression here is the celebrated Schwarzschild metric. This is the exact metric for a perfectly spherical, empty space solution to Einstein's equation outside a star or planet or something like that. And Einstein himself saw it and was instantly impressed. That's memorable because Einstein was handed lots of papers, and he was not usually instantly impressed. He usually had a reason to disbelieve them. For Schwarzschild's solution, he was very, very happy. Now, from here, now you're cooking with gas. Now you can calculate the motion of the Earth around the sun, or more importantly, the motion of Mercury. You can calculate gravitational lensing and gravitational redshift and a whole bunch of other predictions. One of the reasons why Einstein so quickly became a celebrity is because his equation led to predictions which were tested and successful at them. Arthur Eddington led an expedition to look for the gravitational lensing of light during a solar eclipse. It is believed that he was less than perfectly rigorous with the data, but he got the answer that he knew he wanted to get. And Einstein was very happy. But I don't want to talk about that now. We were running out of time, so let me just talk about one fact that you can glean from this equation. I want to let you know that it's not just some symbols here. You can get something out of them. So remember, we have interpretations or meaning for these different components of the metric tensor, right? GTT is the rate at which time flows for an observer compared to the time coordinate, etc. And then you look at this, and you look at GTT, it's the upper left-hand corner, right? 1 minus 2gm over r. R is the radial coordinate, g is Newton's constant, m is the mass of the thing. And you go, wait a minute, when r equals 2gm, this whole quantity equals 0. It's 1 minus 1. So time isn't flowing? Or something like that? What is going on at r equals 2gm? And then you look at the RR component, the next one down, diagonally, and it is, if the TT component was 0, this one is minus the reciprocal of 0, 1 over 0, which is infinity, and that's bad. So as soon as you write this down, you're like, there's something weird seems to be happening at r equals 2gm. So what did people do? Well, they said they calculated the value of r equals 2gm. So you know the mass of the sun, you know the radius of the sun. At what radius are we talking about here? And what you very quickly find is that the relevant value of r, which is now called the Schwarzschild radius, for obvious reasons, is much, much smaller than the actual radius of the sun. And this solution is only supposed to be valid outside the surface of the sun, not deep into the interior. So people said, and correctly, the fact that this metric seems to go haywire when r equals 2gm is not physically relevant for things like the sun, the earth, etc. It only refers to places where the solution is not supposed to be valid anyway. Some more imaginative astronomers said, yes, but what if the thing collapses? You can see a 3-hour biopic about one of them if you go to see Oppenheimer. Oppenheimer and his student Harlan Snyder solved not for the static case, but they allowed a sphere of mass to collapse. And they showed that it collapsed and went right beyond the Schwarzschild radius. So this could be relevant physically. What is it? You all know what it is. It's a black hole. Here's a picture of a black hole. Not the black hole, you know what I mean. It's a picture of the light going nearby a black hole. This is from the Event Horizon Telescope. But here, just to make it vivid, remember, what is G00, GTT? It's how fast time flows compared to the time coordinate. I'm plotting it now. 1 minus 2gm over r, so this is r in units of gm on the horizontal axis, and there's G00. And so you see that at r equals 2gm, this number goes to 0. So at that place, the rate of passage of time experienced is 0. From the point of view of an outside observer, we call that place the event horizon. It took decades of clever mathematical work. It wasn't really until the 50s that people figured out how to just change coordinates, and there wasn't a barrier that you hit at the event horizon. You could just go right through it if you wanted to. These coordinates aren't very good there, but coordinates are just human inventions. They're nothing very deep. And furthermore, there was work by people like Chandrasekhar and others that showed that these collapses can actually happen in the real world. And finally, they started saying in the 50s and 60s, maybe these black holes actually exist. Nowadays, of course, we take pictures of them. We give out Nobel Prizes like candy for people who are observing them in various ways. And the point of this is the last slide, which is that the reason why we care about these equations so much is because the equations are smarter than we are. Albert Einstein was pretty smart. He derived that equation that we show you here in the middle of the slide, but he never knew about black holes. He never fully understood gravitational waves. He was always somewhat uncomfortable with the idea of the Big Bang. The equations just sat back smugly and said, you'll figure it out eventually. And we're getting there. Same thing with Newton's equations or with Maxwell's equations or with Schrödinger's equation of quantum mechanics. We do some experiments locally here in our short, brief lifetimes. We make some leaps of imagination to distill all of this complex physical behavior down to this little concrete poem. And then we blithely extend it to circumstances we haven't even imagined seeing yet. And a good equation is going to teach us something that will go, yep, the equation knew it all along. Thank you.